So hello, everybody. My name is John, and thank you for coming to my thesis defense, which we're calling Reinforcement Learning for Adaptive Sampling in X-ray Applications. I'm going to start by talking about what we want our research to accomplish. In short, we want to use X-ray beams to measure samples for scientific experiments. So, for example, in archaeology, we might want to use an X-ray beam to scan a fossil. By doing this, X-rays can allow us to see things that aren't visible to the human eye, and this can help us make great discoveries. So this is a picture of an actual fossil, and this is a phosphorus scan from an X-ray of the previous sample. And if we look really closely here, if we zoom in close enough, you can see some faint lines that would otherwise be imperceptible to the human eye. These turned out to be an early discovery of quills for feathers on a dinosaur. And then aside from archaeology, we also have history applications. We can use X-rays to study historical art and understand how it was made and some of the changes it has undergone. So for instance, with this writing here, to the naked eye, you just see writing on a page. However, after an X-ray analysis, you can see that there was an original text that actually had gotten written over. And so if we zoom in here, you can see that there's some red letters. Now this is the new text, but then there's also some kind of dark green scribbles. Hopefully you can see it. I'm not sure how the colors come out, but that's actually some older text that had been scrubbed out and written over that they were able to recover with X-ray technology. And then last but not least, here appears to be just a simple painting, but no, it turns out that there's also writing underneath that as well. And this is all possible with X-ray technology. And aside from archaeology and art history, there are many, many other applications that we can apply these ideas to. Some of them are listed here. So we have, a great motivation to use these X-ray beams to conduct all sorts of scientific experiments. So what's stopping us? What's the problem? Well, it turns out that using X-ray beams is pretty expensive. So first of all, there's a financial cost. It can cost hundreds, and in some cases, thousands of dollars per hour to run an X-ray beam line. In addition, there's a time cost, especially for large samples with certain experiments. It could take hours or even days to finish scanning. Not only that, but there is a setup and supervision cost as well. Typically, scientists need to program the X-ray scanners to take the measurements that they want. And in addition to that, they have to supervise the experiments after, and this can be time consuming. And then lastly, it's a research bottleneck. Typically, well, it depends on the application, but in many applications, these X-ray beams are in short supply, and there's no shortage of experimentalists and scientists that want to use them. And so if they're, if the experiments are all very inefficient, then this can end up causing a huge backup. I know personally, I had to wait several months just to have a chance to conduct a live test at Slack. And that's just because the technology is really in demand. Everyone wants to use it. So, okay. So X-rays are great. Unfortunately, they're, very costly to use in a sense. So what can we do about this? Well, it turns out that our solution is going to be to provide an automated adaptive sampling algorithm. So automation is going to allow for less user involvement, and adaptive sampling means that we can create more efficient measurement patterns, which will allow for shorter experiments that will cost less money and take fewer hours. So this is challenging because it's not obvious how to sample efficiently with an X-ray beam. Further, even if we do have an idea of how we might want to sample efficiently, we need a methodology that can scale to very large samples, that can work on real hardware, and can be robust to samples that we haven't seen before. So our approach and main contributions are as follows. We propose a general reinforcement learning framework for producing automated adaptive sampling algorithms, and we provide specific implementation techniques for these following applications: X-ray fluorescence, high throughput X-ray diffraction, and X-ray fluorescence again, but in the live testing scenario. All right. So now I'm going to go over what you can expect the rest of my talk to be about. First, I'm going to cover some background that is relevant for both research projects that I will discuss. Then I'll discuss the research projects that I worked on. And then lastly, I will conclude and touch on some future work. All right, so let's do background. Okay, there are three key areas to understand to appreciate the work that we're doing: adaptive sampling, reinforcement learning, and then the combination of the two. So we'll start with adaptive sampling. Measuring everywhere on a sample, like this animation shows, in a lawnmower fashion works, but it feels wasteful. An alternative is to take measurements to gather info and then use that information to measure only the interesting areas. And that's what adaptive sampling is about. So to kind of give a rough idea of what this might look like, so let's say that we're measuring the sample on the left. We might do an initial fast pass over the image and get, a blurry, not very good low resolution depiction of it on the right. So this isn't very useful for science. However, using these measurements as guidance, we can then conduct a second round of measurements that focuses in on the areas of highest interest, perhaps the areas in red, and maybe we'll ignore the darkest areas altogether. And this is the idea behind adaptive sampling. Also, I should mention that these areas are very related to adaptive sampling. So for anyone in the audience who's already familiar with any of these topics, these are all closely related. All right, so we've covered adaptive sampling. Next, I will move on to reinforcement learning. So in reinforcement learning, we have an agent. So this is a little bit more dense, but I will give an example afterwards. Our agent, probably the AI agent, will interact with some environment over and over. The agent takes as input a state, which reflects the status of the environment. And based on that, the agent then chooses an action. After taking that action, the environment changes and presents a new state to the agent, along with a reward signal. The reward signal tells the agent how well it is doing in the environment. So we can use reinforcement learning to train an AI to take better actions in an environment and get higher rewards. So here's an example. So reinforcement learning can be used to teach AI agents to play games. A very famous example is AlphaGo. So in this example, our state would be the game board. This is the information that the agent needs to make a decision. The action would be placing a game piece on the board. These are all the legal moves that you can make in the game of Go. And then the reward, there's many ways of doing the reward, but for this example, the reward could be +1 if the agent wins, -1 if the agent loses, and then just a neutral 0 if the game is ongoing. And this reward signal will help inform the agent how well it's performing at the game. All right, so that's reinforcement learning. So lastly, I'm just going to touch on how we can combine adaptive sampling with reinforcement learning, which is really the foundation of the work that we've done. So our approach is really straightforward. In adaptive sampling, we choose measurements to take with the X-ray beam in an attempt to measure as efficiently as possible. This is a sequential problem. Reinforcement learning provides us with a way to maximize some reward over many time steps, i.e. sequential problems. So what can we do? Well, it turns out we can just turn the adaptive sampling problem into a reinforcement learning problem and solve it with a reinforcement learning solver. We do this by creating a simulation environment that emulates taking measurements with X-rays and setting the reward signal to reflect measurement efficiency. All right, so this concludes the background section. So now I'm going to talk about some of the X-ray projects that I've been working on. So the first section is variable acquisition time applications. So that might be a lot of words. Basically, what this comes down to is in these applications, we can not only choose the location of our measurements, but we can also choose an exposure time for them, which controls how much noise the measurement has and how fast the scan is overall. So this work is going to focus on imaging applications where we take measurements by scanning a probe beam across a sample. The idea is to take enough measurements to create an image of the sample, often in cases where we want to visualize a signal that is not visible to the human eye. X-ray fluorescence imaging is one application, and there are many others, some listed here. So again, a common baseline approach is to do what's called a raster scan, where we measure each part of the sample for an even amount of time and move the probe beam in a lawnmower-like fashion. However, many samples are sparse in terms of the areas of interest that we actually want to measure. So in this image, we may really only be interested in the highlighted points. Here, raster scanning can be very inefficient, as a single scan of an entire sample can take several hours or even days. So what are the options? Well, first, the beams used for measurement have multiple aperture and speed settings, which we can use to vary the quality and time of our measurements. Beam aperture size controls resolution, and the beam speed will affect the noise. And I have some illustrations of both of those. So the first one is a visualization of different aperture sizes for measurements. So a single measurement is a sum of the sample's intensities in the orange region plus noise. This means that low resolution measurements cover a much larger area, while high resolution measurements are more precise. Here, we can see the measurements of this ground truth sample in the top left for each aperture. Notice how the image is much clearer as we move from low resolution to high. However, as we decrease the exposure time and speed up, note how the high resolution measurements are much more impacted by noise than the low resolution ones. So I actually want to make another point here. So the point is that we have a trade-off here. We have a trade-off between fast, low resolution that's fairly noise robust, and slow, high resolution measurements that are very precise. And we need to combine these in some way to get a good balanced scanning pattern. So instead of raster scanning, we would like to do what's called an adaptive scan, combining the best of fast, low resolution and slow, high resolution measurements. It's possible to focus the costly high measurement areas really in the areas where they're most valuable. So for instance, in this image, most of it's sparse. We may not want to measure maybe 99% of it, but in these areas that I've highlighted here, we would really like to drill down with the high resolution. And so here's sort of a mock-up of what we would like for this to look like. So we have a ground truth sample, and then we would start with a low resolution pass, and then iteratively drill down and down and down until finally we were focusing the high resolution in the areas of highest interest. All right. So this is a little bit of a recap from the previous section, but
That's just
just
a
to
really
remind you,
quick clarification question, which is when you think about location resolution, should I just think of that as specifying the size of the rectangle, or what spatial resolution do you have access to customizing?
it's really just the radius of the aperture. So if we go back to this slide, when we're controlling the resolution, all we're doing is controlling the area of the measurement that we take, if that makes sense.
Oh, but I mean, like when you get to like focus in on parts of the image that are of most interest, do you basically, can you put the center of that anywhere, or like what is the location constraints?
Oh, I see. So you can, but typically we're going to be kind of driving this beam along the image. So you can almost think of it like a car or an airplane that has to fly across the surface of the image. So we can't, what we don't want to do is sort of willy-nilly, like, oh, we're going to measure the top left corner and then immediately after measure the top right. We could do that, but it would just be very inefficient because we have to drive the beam across the image in order to do that. So there is a constraint in terms of making sure that we're carving out a path that's efficient. Ultimately, we're judged by the total elapsed time of the scan and not the number of measurements that we've taken. In a way, number of measurements is sort of irrelevant because you could think of it as taking infinitely many measurements that are all just really, really fast if you wanted to. And so it's really about minimizing the driving time over the image. And so with the high resolution, what that might look like is we might go really, really fast over areas that we know we don't want to measure and then slow down for the areas that are really important. And the slowing down part of it will lower the noise, and that's how we get the value.
Got it. Thank you.
Okay, so let's see. Right, so I went back a lot. That's the problem with having too many slides. So okay, so now So again, so it's important to be able to automate these adaptive experiments. There is a notion that you could do this manually, but it's difficult and time consuming, and it's not clear what's optimal. So we would really like to automate this process as much as possible. So the purpose of this work is to provide a learning framework that can generate automated adaptive sampling algorithms. So I'm going to touch on some key related works though before I jump into what we ended up doing. So there are existing works already that provide methods for doing adaptive sampling. So this work uses kriging, a form of Gaussian process regression to guide sampling. So here, kriging is used to both reconstruct the image from measurements and quantify uncertainty over pixel values, guiding future measurements. And so what this allows you to do is it allows you to make a prediction of the image, but it also shows you areas where your prediction has high variance or where you're uncertain of what the ground truth really is. And that can inform where you would want to take your next measurements. So our approach differs in that we directly train the reinforcement learning acquisition function on simulated and archived data, as opposed to following a Gaussian distribution or any sort of formal prior. And then these are just some plots from the paper. So I guess maybe I could talk about this more, but I think in the interest of time, I'll move past this. But if anyone wants to ask about this later, I can come back. Okay. So then a second important related work is so how do I, hopefully this makes sense, but feel free to ask questions. So what they do is they generate an adaptive sampling mask. And the way they do this is they have a mask generating network and an image impinting network that fills in everywhere that they didn't measure. And they're both trained end to end for XRF applications. So the thing is that the way this works is they take an RGB image, like a photograph of the sample that they want to measure, and they feed that into a neural network. The neural network then outputs a sampling mask, which is sort of like a dot pattern that then the XRF beam is meant to follow. And then once they've collected that sparse set of measurements, they then fill in the rest with another neural network that does in-painting. So that's the idea behind this work. So our approach differs in that we assume no initial measurements, so we don't get the benefit of having an RGB image to get us started. The only input to our algorithm at runtime is the history of previous measurements, which is nothing. Secondly, our algorithm collects measurements over multiple time steps and multiple resolutions, and we vary the exposure time for each measurement. In this work, I don't think they use multiple resolutions, and they don't vary the exposure time, although they do have some ways of working around that, but it's not quite the same. And then lastly, our algorithm does not require a differentiable reconstruction method because we're not training. We treat our reconstruction algorithm as a black box function as opposed to training a neural net or anything that we have specific knowledge about. All right. So going back to our work, so I'm going to go through sort of 3 high-level goals that inform the decisions we made in our methodology. So we have 3 goals. The first one is we want to optimize a general imaging objective. So imaging objectives can differ based on the distribution of samples that we want to measure, the loss metric that we use to evaluate the quality of our final image that we output after we've taken the measurements. There's also optionally the choice of how we convert measurements to the image to begin with. For instance, you could use a classical optimization approach, you could use deep learning, etc. And then ultimately, no matter what crazy set of samples and quality metrics and reconstruction functions that we throw at this algorithm, we want it to be able to maximize expected scan quality. So this is what we mean by it being general, is we would like for it to be able to handle a wide variety of settings. This isn't meant to be dedicated towards 1 or 2 specific cases. So our second goal is that we want to scale to large images, typically represented by thousands or even millions of pixels. And this is challenging not only because of the size, but also because the output space that we have to consider is very large. There's countless combinations of measurements that we can take when we're measuring these images. We have to, for every measurement, we have to decide a location, an aperture, and an exposure time, in addition to the order in which they take place, because the order affects the travel time. Further, our adaptive algorithm has to process a large number of measurements and select future ones quickly because the measurements can be captured on the order of milliseconds. So we don't have several hours to do a computation and then come back with the next wave of measurements. It has to be very fast. Yeah, I think that covered that. Okay, and then lastly, our algorithm must control the beam using low-level controls. So even though we've discussed this work is, we're choosing measurement locations and we're trying to, pick the right set of locations, ultimately the X-ray beam isn't controlled that way. We don't get to just set a location and have it go there. So we actually have to, like I said, sort of drive the beam over the sample in order to get this to work. So it's a small detail to work out in the end, but it's still important to consider. Oh, one other detail here too is that we input resolution switching commands as well. So we have the option to switch between apertures at will, and there is a time cost to that, and that's something that we also have to factor in. So overall, the combined goal of handling a general imaging objective, scaling to large images, and handling low-level trajectory inputs makes it non-trivial to apply many previous works to this problem to the extent of our knowledge. So now I'll describe how we approach these three goals and go a little bit into our methodology. So first goal, we want to optimize a general imaging objective. This is where we're going to use the foundation of the work in this presentation, which is going to be using reinforcement learning to do adaptive sampling. So what we do is we're going to formulate the XRF measuring problem as a reinforcement learning problem. In order to do that, we have to define the states, actions, and rewards. The states are the set of measurements collected so far, the beam position and its velocity. The action will be a trajectory for the beam to follow in order to take measurements. And the reward will be the marginal improvement in our imaging objective. So here's an example of what this might look like. So the state will be our set of previous measurements. So in this case, we have two apertures that we've already used. And these are the measurements for those apertures. The bright spots just indicate areas where we've seen higher signal. And this is typically because what we'll do is we'll slow down and then speed up at intervals. And that's how you get these dot patterns. And then the action will be a trajectory. Now here I represent the trajectory as an image. So I'll explain more about this, but for now, the intensity of this image is just a reflection of how much time we want to spend at that corresponding location. This isn't exactly what we get to execute, but this is a starting point. And then lastly, our reward is going to be the marginal improvement in the image after taking this measurement minus the time cost. So here, if you compare the prediction to the ground truth, we've gotten much better image quality, but we've doubled the amount of time that we spent. All right. Our second goal is we want to be able to scale to large images. So recall that in reinforcement learning, the policy is a function that converts states to actions. So here we propose using a convolutional neural net to process all previous measurements as a multi-channeled image and output an exposure time for each location represented in the input. In this work, at each time step, we use a different aperture progressing from low resolution to high. For each aperture, we query our convolutional net and treat the output as exposure times for the current aperture. So if we had 5 apertures, we would query our convolutional policy 5 times. Each time it specifies how we will use a single aperture. So this lets us manage computation time as querying a network for measurement times is fast, and it grows the way our architecture works. It will grow linearly in the number of pixels in the image. And then this is a visualization of what it's doing. So the key here is that for any spot on the sample that we'd want to measure, we're going to take a local neighborhood of the measurements around that area and then process them through our neural network in order to decide how long that we need to measure. So this is really the key to why this scales well, is because even if this image was twice as big, the amount of computation that we do per pixel stays the same. And that's what allows us to scale. All right. And lastly, we need to optimize over low-level controls. So I'll probably go fairly quickly through this, but I do think it is pretty interesting. So at this step, we need to take this image of outputted exposure times. So remember, our policy is this convolutional network. So it's outputting an image of exposure times, but we need a trajectory. So how do we get there? So what we do is we are going to optimize a trajectory to match the outputted image as close as we can. And it ends up being a little bit of an approximation. So I'll just skip to what it looks like. So if this was the outputted exposure time by our neural network can theoretically output anything it wants to. So there's no guarantee that the neural net output is going to correspond to anything that we could actually run on hardware. The reason why is because, for instance, here, if we wanted to slow down very suddenly after going very quickly, because the black color indicates almost no exposure time, we can't really do this. There's no trajectory that measures this white point in the top right that also goes very fast around it. And so the key is that you have to slow down to be able to do this. And so what we have is sort of this problem is combinatorially hard, so this isn't optimal by any means, but we have a heuristic approach for relaxing the outputted exposure times to feasible exposure times that we can actually run on hardware. And this is actually what we would run in simulation to train our policy. So even though our policy outputs this, its rewards are being judged based off of a feasible trajectory that's being transformed. All right. So that's how we optimize over low-level controls. So now let's take a look at how this performs. So here we see an image produced by our adaptive method compared to some rastering baselines. The black and white images at the bottom represent the adaptive exposure times for each aperture. So the original image is on the left. The adaptive reconstruction is the one next to it. Now, these three images on the right are different rastering images that utilize different resolutions. So resolution 0 is the lowest, blurriest resolution, and resolution 2 is the highest resolution. If you measure finely enough with low resolution, you actually are able to recover higher resolution characteristics of the image. But even then, these rastering methods aren't really able to recover the original dots that we were trying to capture. And then another thing that's fun is that because of the way our architecture works, we can take the policy that was trained on these little images. And by the way, this is very nice because computationally speaking, training on small images is much better than training on larger images, at least the way that we were doing it. But we can still—
I have a really quick question here. What's the
yeah.
loss function, mean squared error on the pixel values, or what is the?
Yeah, for all of these examples, it'll be mean squared error on the pixel values.
Okay, thanks.
Yeah, so we've trained on these small images, but then we can actually test this. So this image is about 4 times larger. It might be larger, actually. Sorry, I'm a little nervous, so the math isn't working out in my head. But this is the original image that is much larger than anything we've trained on before. And then now we're seeing how well our adaptive sampling method can do on a much larger image than it's encountered in the past. And it does reasonably well, especially when you compare it to any of the raster approaches, which basically don't recover any of the dots. And then at the bottom, you can see the measurement patterns and what it's doing. So maybe to explain these measurement patterns a little bit. So the first pass with low res is typically sort of a uniform pattern like what we're seeing. So these dots, so I'm looking at adaptive res 0 in the bottom row. And so these little dots really just correspond to slowing down at intervals to take, a few very good measurements in, kind of a grid pattern. Then after this is when we can start to do adaptive sampling, because now we have a rough idea of what's going on in the image. And then the adaptive res 1 and adaptive res 2 are higher resolution apertures that are slowing down in order to capture the finer details. And then here's just like another type of data, but it's the same idea. So this is what we call the texture data. I like this example because I don't know if this will show for everybody's on everybody's monitor, but in the original image, you can clearly see this contrasty textured triangle, but there's also a very subtle hidden texture pattern in the top. And so the adaptive image does a good job of recovering the triangle, but it doesn't really recover the light texture at all. And so I like this example to show that even though we are using, a learning-based approach and we would like to be optimal, that's not to say that these scans are perfect. You can still miss small details. And so you do have to think carefully about how you're training these policies and what you want them to do. But that being said, it still outperforms the raster imaging. So I would argue that this is preferable to those options. And then lastly, we take a real image that one of our collaborators provided to us, and we used the policy that was trained on these toy examples on the real image to see how it did. And it also outperforms raster on these. So for some, this has all been qualitative results. So for some quantitative results, really quickly here, blue is the adaptive method and raster, or red is the raster approach. And so in these plots, the red is the best of any rastering method. And that's partly why they have some irregular curves. And so really behind the scenes, there are 3 or more curves, and we're taking the minimum to get the baseline for raster, just to keep the plot clean. And so in all of these cases, adaptive outperforms raster, and the different plots just correspond to training on different images and then testing on different images as well. All right. So there are still many challenges with this. So training may require thousands to millions of simulations, and that can be very computationally expensive. And then further, learning difficulty increases with episode length. So this is a point I didn't really get to dive into. But I guess going back here is that we're taking very large sweeps. So every time we measure, right, we're doing a sweep over the image. And so the reinforcement learning doesn't have to think as many steps ahead in a way, because it's doing measurements in a batch. But if we wanted to do, let's say we wanted to query the reinforcement learning every row, for instance, then we have to string together more and more and more actions before we get to the end of the scan. And just in general, that makes it harder to do reinforcement learning. So I glossed over that a bit, but that's the reason why that's there. And then future work, there's so many things you can do to improve this. I guess from a scientific standpoint, we would like to see more complex multi-channeled readings. One nice thing about doing these XRF scans is you can actually read multiple components at once. We can also try more interesting image quality metrics. Mean squared error is simple, but it doesn't necessarily mean that that's what we want to optimize for. Further, we could try to jointly learn a sampling method with a reconstruction method, in addition to more interesting path planning and more creative aperture switching, because in this work, we were very conservative on both of those fronts. And then lastly, you can always have a more complicated neural net architecture or a more clever one. And that's always an area that you can seek to improve in. All right, so this wraps up that first part of the project. And I did want to spend probably the most time there. The second project is, I think, very similar and will go much faster. So I say, so it's 10:10. So I think we have until 10:25. Is that right? Okay. So yeah, so we're on time. I think I will just keep going. All right, so we talked about variable acquisition time applications. That's the hard nightmare scenario because there's so many possibilities to think about. We have to think about the location of the measurements, like what resolution they're going to be, and then the exposure times. And especially the exposure times, like the location and the aperture are discrete at least, but the exposure time is a continuous value. So it's just a very high dimensional decision space to try to explore to figure out how to be optimal. So now we're going to switch from that very complex scenario to one that's a little bit more simple, but still challenging in its own way, which is now we're going to restrict our choice to constant acquisition time, and we're going to focus only on the location of the measurements. All right. So in this setting, images are formed by measuring at discrete points on the wafer. So if you look at this metallic image here, hopefully you can see that there's little squares, little grid cells, and those represent the discrete points where we can take measurements. And then some applications where this could be useful are listed on the left. So the image in the bottom right, by the way, is a classification of the little metal wafer in the top left. And this is kind of a preview of what we'll be trying to do here. So The problem, very similar to the previous work, is that many sample types are sparse and measuring everywhere is suboptimal. So in this case, if we go into this problem with a prior that these regions are contiguous and that there are 5 of them, we don't necessarily need to measure every point to have a good sense of what this image looks like. Some intuition for this is maybe if we just understand where the borders, where the boundaries are between the different classes, that will be sufficient to reconstruct the image. And we don't necessarily need to measure in the centers of these regions once we've identified the outlines. So in this problem, collecting measurements is simplified, but there's still a twist to it. So we do get to choose a position. Also in this example, we don't have to worry about travel time. We can measure freely, the top left, and then the next measurement can be the bottom right. And we don't have to worry at all about any sort of pathing in this example either. However, the noise is a bit more unruly. In the previous example, the noise was quite predictable. In this example, there's a lot. I'll come to this actually. So there's a lot going on behind the scenes, but at the end of the day, we get uniform noise on our measurements, which means that if we're measuring a wafer that might look something like what's on the right, the measurements that we get end up looking like something that's on the left, right? So sort of like a noisy, staticky version of the ground truth on the right. And when we take, this many measurements, this isn't so bad. I think probably most of us can look at this and get a sense of probably what the ground truth is. But the problem becomes when you're trying to be efficient and do a small number of measurements, the noise starts to really make things unclear. For instance, just based off of the measurements on the left, we might feel confident about the green region, the yellow, and the brown, but the 2 blue regions, there's a lot of overlap. They're sort of spread out. It's sort of unclear where to place the blue regions based on these measurements. All right. So again, ideally, what we would like to see is something that takes advantage of the sparsity of these samples. In an example like this, we would think that we could do much better by just exploring the boundary and not necessarily worrying about the points in the middle. And that's the principle that we'll be trying to exploit as we look at the experiments and the methodology. All right. So again, we have 3 goals. This is going to be very similar to the previous approach. So again, we want to optimize a general imaging objective. So this has not changed from the previous discussion. And so again, we want to be able to handle black box image reconstruction functions. To revisit, a reconstruction function is the function that takes the measurements on the left and then creates a prediction on the right. So we want to be able to operate with black box reconstruction functions. Black box, well, not black box necessarily, but more or less black box noise functions on the measurements. And then also a general imaging objective in the sense that in this work, we mostly look at 0-1 loss, but in general, we might want to look at other loss functions or other criterion. And so we want a methodology that can work with all of the above. In addition, for this particular scenario, we want to be robust to the number of classes. I haven't explained this, but in general, we don't necessarily know how many classes we're going to get. Sometimes we do, but sometimes we don't. And so ideally, we would like to have a method that doesn't need to go in knowing how many classes are there. And that ends up being pretty important. And then lastly, we want to be able to scale to large images. All right. So again, how do we optimize the general imaging objective? We're using the foundational idea that underpins this entire presentation, which is that we're combining reinforcement learning with adaptive sampling. And so in this setting, our state is going to be a list characterizing each measurable point. So this is just a way of kind of summarizing all of the information we've gathered so far. And then the action is going to be choosing the discrete point to measure at. And then the reward is going to be the improvement in the image quality minus the cost and time. All right, and so here is a visualization of what this looks like. I don't necessarily expect anybody to make too much intuitive sense of some of these images, but I will walk through it. So these are real images based off of what we're actually doing. And so if the ground truth wafer was something like what's on the left, we have a lot of different characteristics that we can keep track of for each unmeasured point in the image. And that's what this state represents. So I only show 3 images here, but in reality, this is like a 30-dimensional image. It can be, it could be arbitrarily large in a way. We don't want it to be too large, obviously, but there's a lot of channels here because there's a lot of channels of information that you can use to characterize each point in the wafer. And so ultimately, these 3 images at the top are sort of a function. I showed again at the bottom. The bottom is like the measurements that we have currently. So these measurements aren't directly inputted into the state, but these measurements sort of create these feature vectors. So again, these are more for your visual entertainment. These aren't necessarily meant to make intuitive sense. Okay, so that's the state vector. And then the action is just picking a discrete point. So I marked that with a red X. So this is actually roughly where the policy tries to measure. So it looks like it's trying to find a better boundary between brown and green. And then in this case, the measurement was taken. In this case, the prediction was not updated, which happens sometimes. And so the reward is just a minus cost for taking a measurement that didn't improve the image quality. All right, so same strategy for optimizing a general imaging objective. But now how are we robust to the number of classes? So here, the trick is really that we want to use class agnostic state information. And so, like I said, there's lots of things that we can use to form the state. But this is sort of a high level idea of what we're doing. So we can compute distances between points. We can compute measures of agreement, which is like an idea for in a region, how many of the measured points have the same class. So we don't need to know what class it was. We don't need to say if it's this material or that material. We can just decide if they're the same or if they're different. And that's what allows us to be class agnostic in a way. And then we also do boundary detection, edge detection, and then look at the total number of measured points as well. All right, so pretty straightforward for that. And then the last goal is we want to scale to large images, and lo and behold, we're following very similar logic to before. So to achieve this, our policy function is going to apply a ranking function this time, because keep in mind that we need to decide whether or not to measure a single point. We also need to decide in some scenarios when to stop taking measurements altogether. So the system that we use is that our policy is going to be applied to every measurement. We are going to score every measurement. If every score is negative, then we stop. So we do not have an explicit stop action. Stop happens when every remaining point that has not been measured gets a negative score. Otherwise, we will measure the point with the highest score. And then this is what the scores might look like. So again, here's the scary looking state tuple. And then here are the rankings. And so I think there's not too much intuition to this, especially because the white points are points that get that are no longer eligible because of actually wait. Yeah, I think the white points are meant to be the highest value actually. But then we also have mixed in like points that are no longer eligible. So it sort of makes the image sort of murky looking. And then I guess on the border, you can see there's a little bit of a difference there. But aside from that, this isn't meant to be very intuitive. This isn't another thing that I want to mention here is this isn't necessarily to be confused with a value map. So this isn't necessarily calculating the value of a measurement, right? Because it's not being optimized to do that. All it's trying to learn is how to order the measurements in an ordering such that the measurement that has the highest rank is the one that we want to measure. That does not necessarily mean that the rankings that we see are reflective of any sort of value holistically, if that makes sense. Although, maybe it's a reasonable hypothesis. Okay. So that's how we're scaling to large images, is by using that architecture. And then finally, okay, so this is the fun part for me, is I'm gonna share some results here and then I have to move on. But this project has had a lot of ups and downs. We tried a lot of different scenarios. I'm only gonna show 2, and I am cherry picking for the ones that I think are the most interesting. So just know that we had plenty of other scenarios that weren't so interesting. But again, so this scenario, so remember, we can use a black box reconstruction function. So what happens if we decide to use a bad reconstruction function? What if somebody wants to use nearest neighbor classification? So what happens here is you can see this is a pretty, so I should explain, the red points are where we have measured. And so what's happening here is that everywhere that we measure a point that doesn't have noise, for instance, in the top right, we measure brown pretty consistently, then the prediction matches the image and everything's fine. However, when we do get a noise point, like in the bottom left, you can see we got a dark blue measurement. That noise really impacts the prediction for single nearest neighbors. And it creates this horrible amalgamation of colors that doesn't really belong. But what's really interesting to me is that the reinforcement learning, again, treating the k nearest neighbors reconstruction as a black box, given the opportunity to take more measurements, can actually start to overcome some of the flaws of one nearest neighbor's classification, to the point where what it starts to do is identify noise points itself and surround them with measurements so that it forces k nearest neighbors to do the right thing. And I just think that's so cool that it does that. And then this is sort of the final version of it, which is that it will surround all the noise points with measurements, forcing one nearest neighbors to produce a reasonable prediction, which maximizes our imaging objective, which is what it's trying to do. And then here's sort of a comparison plot. So again, this is compared to random sampling, and random, there are other baselines as well, but random ends up being comparable or better than other things that we've tried. And so again, the thing that's interesting to note here is that the learn policies stop measuring, right? So if we look here, this was actually trained with 0 penalty for taking measurements, but it does stop measuring. And the reason why is because it knows that there's a risk of getting a noise point that corrupts the image, so it doesn't bother. And that's why this stops here. So I guess I'm running out of time, so I can't, sing about this too much, but this was probably my favorite result for this work, because I think it just showed the potential to be flexible. All right. So then here's more relevant work is here. Michael helped me come up with a heuristic reconstruction function that performs pretty well empirically. And so this is a much more reasonable approach to the problem, where we're not handling noise in like an obviously foolish way. And so I'm going to go very quickly through examples here, just out of the interest of time. So what I want to stress is the top is the adaptive scan and the bottom is random. And what you'll notice is that the top scans will start to trace out the boundaries of the image, and they're also much more sample efficient. So the adaptive scans are going to be using 2/3 of the number of measurements that the random scans will, but the adaptive scans will either perform similarly to or will outperform the random scans. So here they're actually tied. But then as we allow the adaptive scan to take more measurements, it starts to pull away. 189 versus 283 measurements, but the loss is higher, even with more measurements. And then here, with almost 400 measurements, it's barely starting to catch up to the adaptive scan, which does a pretty good job of tracing the boundaries, in my opinion. And then we see, so this is trained with only 3 reinforcement learning policies. And so that's why you sort of see like a small blue line here. So this is for the adaptive policies, that's the blue line. And then I did just enough random baselines to sort of show comparable number of measurements and comparable error. So you can see it's pretty strong here. So then one last thing is we wanted to generalize to arbitrary number of classes. So here, it's never trained on anything more than 5 classes. I just decided to change it to 7, see how it does, and it does fine. So even when we up the number of classes or see more classes than we expected, we're still able to perform with the adaptive scan at the top, which does much better than the random scan at the bottom. And then we can also scale up in terms of the density. So if we quadruple the size of the wafer, we can still get good performance with the adaptive scan, even though it's only been trained on small images. So again, training requires lots of simulations, and representing the state and the policy is non-trivial. There's definitely some thought that goes into that, and certainly there's probably going to be better ideas than what I did that will come out in the future. And then future work, there's again no shortage of opportunities to improve performance here with different architectures. We could also focus on using better reconstruction functions. This was its own crusade. Better state representation, the list goes on. But now we're finally done. Thank you so much for listening to me talk about my research projects for so long. I'm just going to go through just a quick conclusion. Let's talk about some future work at a high level, and then we're done here. So I just want to stress again, the main takeaways, if my voice is like soothing you to sleep, the main things to remember is that in X-ray applications, we want to do adaptive sampling for efficiency. And the point of this is that X-rays are incredible for scientific experiments, and we want to be able to do more of them. And so one way of doing that is to lower the amount of time it takes. And that's where adaptive sampling can really shine. Second, we propose general formulations. The idea is we don't want to get too focused on a particular way of representing uncertainty or reconstructing the image. We want to be able to handle a wide variety of settings so that this methodology can be used for a wide variety of applications. And then finally, our implementations outperform the random/raster baselines, which just shows that they have some viability, and with further refinement could perhaps be much, much better. So future work, again, I've said this so many times, methodology can be improved. Also, we can do live testing, i.e. sim to real. All of the work I showed today was in simulation, but it's another step to take simulation results to actual hardware. And then also we discussed, 2 applications, but there are many others that could be considered as well. And then lastly, I hope that we can continue to develop these adaptive sampling algorithms. I believe that they have a lot of untapped potential, and future researchers will be able to achieve much more elaborate and efficient sampling algorithms using these and similar methods in the future.